Good morning, everyone. So let's kind of tackle today's notes. I'll try to do it on the whiteboard when I can, but there's some information. I got a really bad glare here, and I don't know where it's coming from, or shadow. So I'll do the best I can to keep my hand out of the way. So when we're looking at this, and we're starting to get in deeper into the information that's going to be required of us for the AP stats test. So we're dealing with percentile. Okay, so I'm gonna answer this question here. A student's percentile matches the same as percent correct. So that's the question. Are they the same? So if we take a test, let's say we take a test like this, and we've got 40% down here. Somebody didn't do that good. 75, 73, 81, 90, 91, 92, 93. Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And let's make it 11, 99. N equals 11. So that's the number of data points that we have in there. And let's say we look at 73% here. So this person got a 73% correct, but that's not their percentile, because their percentile includes anything. So the percentile includes less than, let's see, includes less than or equal to. All right, so the data point. Now, in your book, it says just less than, but they've updated it to say less than or equal to. So how do we figure out percent? Well, we're going to divide it by the total data points, right? So we know that it's 11, okay? So we know that it's 11, but how many are less than or equal to? 1, 2, 3, 4, 5. So we go 5. So this is going to be less than or equal to the x value, or the point we're looking for. And so if we do 5 divided by 11, we're going to get, so clear, 5 divided by 11. Oops, that is not how you do that in a calculator. 5 divided by 11 gives us approximately the 45th percentile. Oops, let me rewrite that. 45th percentile. I cannot spell percentile. Sorry for the squeeze. That's why I like working on the whiteboard, but we don't have that today. So basically, all we're doing is finding what we're looking for. The data point we're looking for, we're counting the number of data points below it or equal to it, and then we're dividing it by the total number of data points. That is percentile. And I can't even spell that, percentile. So our percentile is not the same as percent correct. And that's how they do the standardized test scores, which I don't think you guys had to take last year anyways. But when you get something that says you're in the 77th percentile, that means that you ended up on the 70, you have 77% of the people did as good or less than you. And that means 33% of the people did better than you guys. So that's just kind of all percentile means. So you guys can calculate this. If you want to turn off your camera, you can. But we're going to calculate the number of wins. So there's 30. There's my N. N equals 30. 30 points. Here's my key. Don't forget, this is 5, 9, 59. So they're going to calculate and interpret the percentiles. I'll let you guys turn off the camera now. 1, 2, 3. So if remember, it's equal to. So if you count them up, you have 25 of the that had 92 wins, 25 of the 30 for the Rockies. And so that means we are at 25 divided by 30 sets us at the 83rd percentile. Okay, so if we're at the 83rd percentile, what does that technically mean? That means that we are looking at 83% of, so this means 83% of the teams had equal to or less number of wins. Okay, so that's your statement right there. We're just talking about how, or fewer, I should put, or fewer. Let's change that to fewer. So 83% of the teams had equal to or fewer number of wins than the Rockies. Okay, so that's our statement that we need to make right there. So if we slide up a little bit here, you guys can look at the other ones. We have a 30 out of 30. So we have the 100th percentile. And then the last one's a little tricky because there's two of them here. So if we go 1, 2, 3, 4, 5 teams, so we're going to go 5 out of 30. And then that's going to give us 5 divided by 30. We're going to get about the 17th percentile or the 16th percentile. So that's how we calculate percentiles. All right. So if we move on to the next piece here, this is called a cumulative relative frequency graph. Cumulative relative frequency graph. All right. So basically all it means is that we run percent over here. So this is percent, this is 80%, 60%, 50%, 20%, 0%. And this is the median income and household. And this is actually in thousands of dollars. Okay, so it's in thousands of dollars here. Now, what happens is we want to know what California with a median household income of $57,445 is at what percentile. So if we go to 57,000, we're technically going to use a straight edge or estimate it the best you can. So we're just going to go like 57,000 takes us up here. And if we look across, that's going to be right around the 80th percentile. So this is California's at the 80th percentile. Okay, for median household income. Now, if we look at the 25th percentile, the 25th percentile is going to be here. We're going to go across, come down. That's $45,000. $45,000 is the median income there. And that is that's the median income, but for this particular graph, it is Q1. It's a quartile 1 because it's got 25% of the data below it. Okay, so the other name for this value is quartile 1, and the 25th percentile is $45,000. All right, let's go ahead and slide up to the last part. So where is the steepest part of the graph? Right now I'm looking at it. It goes from right about from here. Oops, let me go back down here, guys, so you guys can see it. From here to right about there. So that's the steepest right there. Okay, now what does that represent? Well, that represents the higher frequency of the data. Well, what's the big deal? Got to keep my left hand out of the way, guys. Sorry. Higher frequency of the data. So what's the big deal about that? That tells us most data points are right here. So most data points are located between, let's look at this, 40,000 and let's go up to the top here, 55,000. And if you look at it, how much of the data? Well, let's go. We're almost, let's call that 5% here. Let's call that 5%. Let's call that 5%. And let's call that 75%. So we're looking at roughly 70% of the data falls between those two numbers. That pretty much kind of indicates that it may be all the data is on the left, so it may be a skewed right format. So it tells us possibly shape also. All right, so here we go, guys. Trying to make this as painless as possible. All right, so if we're looking at this here, let's look at some of the information. This is a big concept we got right here. So Macy is 100 centimeters tall, and Brody, her 12-year-old brother, is 158 tall. So we've got two pieces of information. Obviously, Brody's taller, blah, 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 blah. We're talking about that is relative to other kids in the same age who is taller. This is where standard deviation comes into play. So we have a mean of 94 for females. So let's just do the females here. And I'm going to write 94.5 right there. And I'll do a little number line here for you guys. Okay? And then a standard deviation of 4. So we're going to go 4 this way and 4 that way. So if I go, this is 90.5. So I subtracted. This is 98.5. Okay? And if we add 4 more, this is going to be 86.5, and this is 102.5. All right. So if we look at the males, I'm going to go ahead and put it in the same spot. Males, the average is 149 for his. This is centimeters. And if we draw our number line, the standard deviation is 8. So now we're at 157. We're at 141. Do one more. 7 plus 8, that's 165. And this one here is 8, 133. So let's go ahead and mark Macy. She is 100 centimeters tall. So she's right there. Okay? And then let's go ahead and mark Brody, who's 158. So relatively speaking, based on the average here, Macy is taller relative to the other kids the same age. Even though her brother Brody is definitely taller than she is actually taller than most kids her age, because she is approximately 1.8 standard deviations away, and he is maybe 1.1 standard deviations away. So that brings us to our next major calculation. This is called a standardized score. It's a z-score, okay? So we're going to say that z equals our x value minus our x bar, which is our mean, divided by our standard deviation. So let's just take Macy's. Macy has an x of 100 centimeters. We subtract her 94.5 average for 3-year-olds, and we divide by the standard deviation of 4. So if we do that, let's see if my estimation was close. 100 minus 94.5 divided by 4 is 1.375. Okay? So we'll see. I just estimated. We'll see how close it are. So let's do the Brody. So we're going to do Brody, which is 158 minus 149 divided by 8. So let's look at that. 158 minus 149 divided by 8 is 1.12. So there are no units on these. Okay, there are no units. And then that's why it's called the standardized score. It gets rid of units. So this is really standard deviations is what this represents. So she is 1.3 standard deviations above because it's positive, and he is 1.125 standard deviations above. If it was negative, that means it would be below. So negative means below. Oops. Below. And positive means above the mean. Okay? So that's what your signs tell you. All right, so let's tackle this here. So here's an age-old question that happens here. We have Babe Ruth, Roger Maris, Mark McGwire, and Barry Bonds. If you notice, you got 1927, 1961, 1998, 2001. They didn't play nearly as many games in 1927. And as you gradually get here, they call this the enhanced age where there's steroids and everything else, and these guys didn't have it here. So as we look at this, we have to make a comparison of each player's standard deviation or each player's z-score. So why don't you go ahead and do that? I'm going to go ahead and do that. So if you want to stop the video, it'll be a question here. You guys know that's coming. And so we're just going to set each one of these up for you guys. So we're going to do their X. This is Babe Ruth minus 7.2 over standard deviation of 9.7. Okay. And so this is Babe Ruth. And then we have Roger Maris, who is going to be 61 minus 18.8 over, oops, just lost the lights, guys. Oh, good. It's no shadows. Maybe that's what I got to do, just not do the lights. 13.4. And then we have Mark McGwire as 70 minus 20.7 all over 12.7. And then our last one, which is Barry Bonds, who hit 73 home runs, and the average was 21.4 all over 13.2. So if we calculate all those, we're going to do 60.7, 60 divided by 7.2, and that's going to give us a value. And then we are going to do each one separately. So Babe Ruth is at 5.44, and then I lost all my lights. It's always fun around here. So here we go. Let's see if I can get it back. All right, guys. Here we go. All right, so now the shadow's back, but sorry about that delay, guys. And if we go through that all, we end up with Maris has 3.16, and McGwire has 3.87, and Bonds has 3.91. So we can tell by far, by far that Babe Ruth is 5.44 standard deviations above the average. He is 2 full standard deviations above anybody else when it comes to hitting home runs. So technically, a lot of people say that he is the greatest of all time because he hit so many more home runs than anybody else during his time. Now, they hit 73, but this was in 1927 and this was in 2001. The only way you can compare them is using standard deviation, and that's why they call it a standardized score. So here's another one. Again, we're using that formula Z equals X minus X bar over the standard deviation. And this is the biggest part of algebra you'll have to ever use. So it asks Mark Grace's total home runs hit. So we know a few pieces of information. We know that his z-score is 0.48. We also know, oops, sorry, that goes here, negative. We'll just scratch that out. This is going to be negative 0.48. His x is what we're looking for. If you go back to the previous problem, x bar in 2001 is 21.4, and the mean is 13.2. So we're just plugging it in, and then we multiply, this is equals right here, we multiply negative 0.48 times 13.2, and then we're going to add that to 21.4, which is equal to x. It's just an algebra problem there, guys, and that's going to give us whatever total that gives us. I don't know off the top of my head. So negative 0.48 times 13.2 plus 21.4. He hit approximately 15 home runs. Okay, so that's how you use standard deviation, guys. We'll talk to you soon, and see you tomorrow.